Hello.
Hi, could you hear me?
Yeah, I hear you pretty well.
Okay,
Yeah,
great.
wait for other people. There will be probably other people interested too.
Because I'm using my iPad, so it's not easy to.
Yeah, it's clearly probably not.
Because I'm at home now.
Oh, okay, nice.
So
So am I.
the camera is not working very well.
I think a camera is not the principal thing here. The main thing is the main feature is to share the screen. So if you can share the screen, that's okay. The camera is just secondary feature here. Of course, it's nice to have a camera, but not crucial. Okay, wait for other people. I know that Professor Zhiglov will go into to join us in a few minutes. I just talked to him, and I know.
Let me. Okay. Probably let me stop the camera and. So we begin in 2 minutes or wait longer?
I think we need to wait at least for Professor Zhiglov, and I also hope that there will be other people coming, but I'm not sure about this, unfortunately. Send this invitation to everyone, but there are some people who I know that they're, for instance, ill and so on. Some of them have too many things to do. We have sometimes some random people who come from the list if they find this actually important for them. Like last time we had Professor Mikhailov from England who joined us because he was interested in the talk by Professor C. And I shall wait.
Yeah. And nowadays there are so many, online.
Oh, here is Dmitry Gurevich. Здравствуйте, Дмитрий Ильич. Okay. Yes, we see people are joining us. Okay, nice. Let's see what else we have here. Здравствуйте, Дмитрий Ильич. Вас плохо слышно, но чуть-чуть совсем слышно. А как вам слышно? Напишите тогда. Если вам слышно хорошо, это нормально, потому что, если будет вопрос, вы просто можете писать, скажем, в чате. Потому что ваш звук, к сожалению, не очень хорошо слышен.
Я спрашиваю, когда ты встречаешься?
Понятно. То есть, видимо, связь не очень надежная, ясно. Окей. Дмитрий Ильич, вы не знаете, Паша к нам присоединится?
Не знаю.
Ага, понятно. Надо дождать немножко. Потому что вроде бы Паше это тоже должно быть интересно, Паше. Вот Саша же.
Да, наверное.
Ага. Так.
Алло.
Здравствуй, Саша.
Здравствуй, Коша.
Подождем у кого-то еще, как ты думаешь?
Конечно, я надеюсь, что это к нам присоединятся. Джунху, я смотрю, здесь.
Замечательно.
Зиран еще позови.
I'm here. This is my name in Chinese character. I didn't change it.
Yeah. I just told about that. Yes. I said that Ziran can also join us.
It's strange he's not here. I really.
Probably he has not yet joined us.
Yeah, there's some problem. I know that he has some.
And Sasha Orlov, I can maybe he can also.
Sasha Orlov has problem with his computers. Sasha Orlov is a very funny person. He has constant problems with computers.
Still. Well, I mean, he could probably connect also with his iPhone.
That's possible. That's also an option. Okay, I just tried to call Jiran right now. Yeah, but this and I need to turn off VPN.
And also my student also joined. I mean,
Yeah, we need to wait a little bit. Sorry.
yes. Pavel.
Is he here? Is Pavel here? I don't see him.
Not yet. Because usually he joins later, probably because he has seminars now until 6 p.m. Because earlier we began at 6 p.m. but now we start at 5 p.m. And this may be crucial because if he has some special course right now, then he need to wait until 6 p.m.
Oh, I see.
He will join probably later.
I just hope so. Так, я думаю, что Павел... Yeah, I see Professor C here. Just I'm sending a message to Deran. I don't know how to pronounce his name. I'm sorry. I don't see him. Don't know. He's staying in quarantine and he's going to be released from quarantine tomorrow. So maybe he's celebrating. I'm not sure about this. He might be celebrating this. Да, Дмитрий Ильич. Вас плохо слышно, Дмитрий Ильич, извините.
Гоша, Паша Сапонов, он будет?
Я вот тоже спросил Дмитрия Ильича, не знаю, Дмитрий Ильич, я не знаю. Паша, он, и в принципе, ему должно быть интересно, но он может быть занят. У него иногда какие-то появляются неожиданные дела в это время.
А сейчас слышно, нет?
Сейчас вас слышно, да. Сейчас вас слышно. Какой-то был вопрос у вас? Okay, let's wait for 2 more minutes and then we'll start.
Of course.
Okay. Meanwhile, you can try sharing the screen with us. Okay.
Okay, then probably I just switch off my camera because I'm using the iPad.
Yes. Okay.
Convenient to use the camera. Sorry for that.
No, don't worry.
Let me try to share the screen. And I guess now you can see my screen, right?
Oh yeah, now we can.
Great. Yeah. Okay. And in case I lose the internet, please WeChat me. Please send a message on WeChat. Yeah, it happens, time to time. So
yeah, just 1 more minute to wait. Oh, so somebody has joined us. Володя Рубцов is here. Здравствуйте, Володя.
Здравствуйте. Он все еще соединяется.
Ну да, он через iPhone, и поэтому это может занять некоторое время. Okay. Okay. So in any case, I think it's time for us to begin. So today's speaker is Professor Xiaoman Xu, right?
yeah.
I'm afraid I'm mispronouncing it. And the subject of the talk is representations of quantum groups arising from the Stokes phenomenon and their applications. Yeah, let us listen to it. So we are all listening. Okay.
Okay, thanks for the introduction. And I would first of all I would like to thank the organizers to invite me. It's my great pleasure to report my recent work, which is about Stokes phenomena and the quantum groups. So I don't assume that everyone is familiar with Stokes, the so-called Stokes phenomenon. So in the first part of my talk, I'm gonna give I guess now you can see my writings, right?
Yeah.
Okay, great. I gonna give a sort of detailed introduction to what is a Stokes phenomenon. So if you go to Wikipedia, it says that the Stokes phenomenon describes the phenomenon that a function on a complex plane, say Fz, can have different asymptotic behaviors as Z goes to a critical point from different directions. So this is a very rough idea what is a Stokes phenomenon. But actually, many, if not all of them, many special functions like Kummer functions, exponential functions, array functions, or Poincare functions have such phenomena. And today we're gonna focus on a class of functions which arises from solving the following linear system of ODEs. So this is our focus for today. And I'm gonna give an introduction to its Stokes phenomenon. So here, this is of course a linear system of ordinary differential equations with a pole whose coefficient one can see has a pole of order 2 at z equal to 0. And I assume this is a n by n system. And where I assume this, I make the assumption that the most singular part, this diagonal matrix, this U is a diagonal matrix, and with distinct diagonal element. So this is, here I use this H to denote the space of Cartan subalgebra. So here I'm talking about type A case. So H is a set of diagonal matrices, and reg means a regular element. So here this U1 to UN are distinct, while A is an arbitrary element inside GUNC. And this is a equation for a function with value in GUNC. So we are talking about the fundamental solutions. In the following, let me recall how to solve this equation, how to find the solutions with prescribed initial conditions, and then introduce this Stokes phenomenon. Okay. So how to solve this equation? Because I guess Professor Sharikin told me that I have 1.5 hours, right? I just want to make sure that.
Yeah. It's Russian tradition to have 90 minute talks. Yeah. So you're free to use all these 90 minutes if you want.
Okay, great. Yeah. I just okay. Then probably I should say more about this introduction part. So I gave a bit more details. But please interrupt me if it's not really necessary. If I give too much details on this ODE side. Yeah. In any case, so how to solve this system? So we can first find that there exists a unique formal solutions of this system. Formal solutions which take the following form. So this is a formal solution where, so this identity is an n by n identity matrix, sort of as an initial condition, plus H1 is an n by n matrix. So this is a matrix valued power series times exponential minus U over Z, and then times Z power of bracket A. So this is a diagonal part. Here is bracket A, simply takes this. I use bracket A to denote the diagonal part of matrix A. Yeah. So here I note that the power of bracket A is a multi-valued function. So here one should take a branch of log z function. Yeah. And if we assume a formal solution takes this form, then as you plug in the expression to the ODE, we can get a recursive relations for all the unknown coefficients, H1, H2, and so on. So one can easily find out the recursion relation is given by the following identity. So here the HM plus 1 terms bracket with diagonal matrix U equals to H multiplied by HM plus A matrix A times HM and minus HM and bracket A. Yeah, we simply plug in the formal solution and to get the recursive relations for the coefficients. And simply from this expression, one can recognize that the growth, the norm of the matrix norm of HM is roughly some constant times constant k power of m and times m factorial, right? Because this factorial term is simply from this m. So if we ignore the last two terms, we see that HM is more or less m factorial growth. But somehow we have another term here. And this k relies on the norm of matrix A and bracket A. So roughly speaking, you get the growth of the norm of HM is some constant power of m and m factorial. So that means
this never converges. This.
Yes, exactly. Yeah, as you pointed out. So in general, this H hat, which denotes the formal part. So this formal sum is generically divergent. So roughly speaking, it's never convergent. So we only get a formal solution. Yeah. And now let me recall you how to use the so-called Borel-Laplace transform to, to get the interesting holomorphic data out of this formal sum. We can do that simply because, although this solution is formal, but it's equivalent to the equation itself, right? Yeah. Mm-hmm. The configuration of the equation is U and A, and the configuration of this formal solution is also U and A, roughly speaking. So it includes all the informations of the equation. Therefore,
just wonder, so it seems that there is a unique formal solution, right?
Yeah.
Doesn't it mean that there are no other solutions? Uniqueness, because any solution which can be written well, which is kind of somehow say analytical, it should be given by this formal procedure. And since this formal procedure gives you something divergent, explicitly divergent, it means that you don't have any analytic solution at all.
Yeah, that is what I'm gonna say. So here, unique means there is a unique formal solution with a given initial condition. So this is really the initial.
Sorry. So this is the initial condition which you can play with.
Exactly. Yeah. Given this initial condition, you can.
Isn't it still possible that the other two factors can compensate so that the overall object is well determined? I mean, this H hat is divergent, but e to the minus u over z and z to the power a can compensate. This question about the analytic solution, I mean, isn't it possible that this can happen?
Yeah. I don't think so. Yeah. I gonna tell you how to do the Borel-Laplace transform of H hat to get a finite sum, to get an actual solution. Yeah. This is a so-called So although this is a formal sum, but still we have a sort of classical method, so-called Borel-Laplace transform, or also known as Borel resummation method, to get holomorphic information, to get holomorphic functions out of this formal power series. So the idea is, if you know it, then the idea is somehow simple. So let's rewrite this formal sum. And the thing is that now we divide each term by k factorial and then times k factorial. Then we do nothing, but somehow we replace k factorial by gamma k plus 1. So this is, we use a gamma function. And of course, we know that the gamma function has an integral expression. So it's the integrand is exponential minus t and then t power of k maybe. And the integration is from 0 to infinity along some direction d. And therefore, we can replace this gamma function by an integral. Then it ends up with something like this. The summation is still from k to the k bigger than 0, and then we have integration from 0 to 1 along some direction d, and the integrand becomes this guy, k over k factorial t power of k. So here I simply replace gamma function by this integral. And here I have 1 over z. Here I implicitly make a coordinates transform just for convenience. Yeah. So I introduce a new t as a old t times z. Then I end up with this guy.
Sorry, can I just ask, the gamma function, when you wrote the gamma function, you put a d in brackets. I mean, this is just integration along r. But I think that d is needed on the second line because you're integrating along the direction defined by z.
Exactly. Yeah.
So the first d is redundant. The first d is not, shouldn't be there. The first d is missing.
Yeah. So here you are right. To be more precise, this direction is only needed in the Borel-Laplace transform, the Laplace transform part, right? Yeah. And another thing is that we formally, so the next identity is where the resummation comes from. So we formally shuffle, switch the summation and the integral. Then we can get, formally we can rewrite this as exponential 1 t over z, and then I put the summation inside, which gives us this term. Right, and now let me denote this part by a new, let's call it GT. I'd better to use a different color. So, sorry. Let's denote GT as HK over K factorial T power of K. Yeah. Okay. Now see, the good thing is that as we already seen, the norm of HM is K power of M times M factorial, which means that the new function, the function we just defined, GT has a, has a non-zero convergent of radius around t equals to 0, right? Yeah. So the estimate shows that GT, here we can say that GT is indeed the holomorphic on the Borel plane, on the T plane, near the T plane, near the T equals to 0. Okay. Another thing is that, let me draw. Another thing is that the integral here, as you just pointed out, so here we take any direction, we take some direction d. Let's say the direction has a certain argument. Another thing is that, so this is on the T plane. We already know that the matrix function GT is holomorphic near 0. And now if further, if further GT can be analytically continued to some sectorial, like continued from 0 to infinity along the direction D, say continued to this region from 0 to infinity. So here I use this to denote a sectoral region with bisecting direction D and with opening some positive real number epsilon. Then, and at the same time, so this condition, this first condition, if GT can be analytically continued along direction D, then we can at least the function, the integrand is defined on the path, right? It's on the integral path, but somehow it may be, blow up. But if at the same time, we can guarantee that GT has exponential type growth as D go to 0 along direction D. For example, if there exists constant alpha beta such that this condition holds, then the integral above, so this integral actually exists and gives a holomorphic function of Z for some for Z in some sectoral region. Yeah. Now let me introduce a name for this integral. Let's call it B of D. I use this index to D to denote the direction where the integral is taken. So BD of H hat. So this is what I defined by the right-hand side, by the integral. Yeah, as I just said, if GT can be analytic to infinity along the direction D and at the same time has a exponential type growth, then we will recognize that BDH hat of Z is simply, let me just rewrite it. Well, do exist for some D, for exist for some Z. Yeah. Now let me tell you for which Z. So is it
also true?
Mm-hmm.
Is it also true that now, once you have fixed this direction, that this equal sign in quotations becomes correct? This question of uniform continuity, is it actually now? You remember when you said you're doing this, you interchange the summation and the integration. Yeah. Does it now? Has it become correct now, or is it still?
No, this
only at the formal level.
Okay.
I'm just curious about this.
Yeah. You are right. So sorry, I simply define. So here I introduce or I define if the right-hand side exists, then I define the borrow transform along direction D of H hat as this guy. And now I haven't told you what are the relation between this integral and the form sum. And later on, I'm gonna say that the integral, the borrow sum, if exists, do have the formal H hat as the asymptotic expansion, in the right sectoral region. Sorry, this is not, of course, this is not equal. This is not equal to. Here I just, here I just give you the idea of where the resummation comes from. Then I should say this is not equal this is not equal now.
Not even in
after
the
giving
sector that you found. Not
Yeah.
even in this sector SD that you found.
Yes. It's not equal to. Yeah. I gonna say it now. Yeah. Okay. I simply introduce this integral. I call it BD H hat. And now we are discussing when this integral exists, right? And for which sort of z, let's see. So for this, I mean, for what kind of z the right-hand side exists, the only condition we need, because we already know that gt is bounded by alpha times exponential power of beta t, right? Therefore, the integral is bounded by something like exponential. So bounded by exponential minus, sorry, let me see, beta t and minus t power of z as t go to infinity. Therefore, for the integral exists, we need the real part. We need the projection. We need the real part of this guy somehow. So we need, because this is along the direction d. Therefore, we need the projection of this guy to the direction d to be negative, right? For this to exist as t big, as t go to infinity. That gives you the region where the integral exists. Yeah, and then you can figure out that this is actually a sectoral region with opening pi. And just in a summary. Yeah, sorry. So this is let me call it a theorem or proposition. So first, take the so-called anti-Stokes race. Now I'm telling you that for which kind of direction d, the right-hand side indeed exists. That is, for which direction d, the function gt can be analytically continued, and at the same time is bounded by exponential power of t. Yeah. And to introduce this direction, I first introduce the so-called anti-Stokes race, and these are the directions pointing to ui minus uj. So here recall that this u, in our equation, we have a diagonal. We have some term u over this square, and I assume u is a diagonal matrix. So its eigenvalues are u1 to un. And here I simply take the difference of ui and uj, and I point it on the complex plane. Then I draw the row from 0 through each of these ui minus uj. Then using this, of course, I get finitely many such rays, and I can cut my complex plane using this rays. And furthermore, let me label this rays by, let me just give a labeling of these rays, label them by d0, d1, and so on, d2l minus 1. There are even numbers of them in a positive sense. So for example, I can call this ray as d0 and then d1, and there are many of them. And this is dl minus 1, dl, and so on. Yeah, I simply label them. Okay, and then now the proposition says that, so this follows from a general theory of meromorphic ODE, in particular in our case with a pole of order 2, Poincare rank 1. It says that if the direction D doesn't coincide with one of the anti-Stokes rays, that is, if D is not equal to DI for some I, then the Borel-Laplace, the Borel transform, the Borel resummation along the direction D of H hat is actually a holomorphic matrix valued function inside the sector, or let's say on the sectoral region S d pi. So here is S d pi is a sectoral region with bisection direction D and with opening angle pi. So if I draw my direction D using this red ray, then this region is simply, it's a sectoral region like this. And this is not hard to prove. One can simply make this. One can simply prove that for the given direction D, this estimate is true by using some, for example, by rewrite this recursion relation as the integral equation, and then using some standard iterated method to show it. Okay, so this is the first result, and the second thing is the second thing is that the Borel transform is compatible with, the Borel transform is sort of a resummation. So it doesn't touch the variable z at all. Therefore, it's compatible with taking differentials on z. That means whatever differential equation H hat satisfy, then the BD H hat satisfy the same equation. Therefore, it implies that FD of z, which is a matrix valued function defined as BD H hat, the function we just got from proposition 1, and times the singular part exponential y u over z times the power of a is actually a holomorphic, or it's an actual solution of our original ODE. Let's just call it the ODE because we only have one ODE in this talk. And this is a solution defined on the same sectoral region as d pi. Yeah. So here I simply use the fact I just said. So the Borel resummation is compatible with taking differentials with respect to z, and this can be easily seen from the integral expression. Yeah. Okay. And now we have two more interesting, important statement which answers one of the previous questions. So another thing is that this Borel, this holomorphic matrix valued function, what's the relation between this BDH hat and the H hat? And actually, the third proposition says that the BD H hat has H hat as a symptotic expansion within as they go to 0 within the sector as d pi. Yeah, it simply means that if we take the Taylor expansion of this matrix value function with inside the sector as d pi, then the Taylor power series is exactly given by H hat z. So this justifies the relation between BDH hat and H hat. Yeah. So from H hat, we do the Borel transform.
So again, can you repeat this about Taylor? I didn't detail the series. So what do you do with this? Can you repeat this again? What does it mean that it's symptotic?
Yeah. So it means that H hat is a asymptotic expansion of BDH hat.
Yeah.
And it equivalently, it means if we compute the Taylor expansion of BDH hat, in the sense that we only allow Z go to 0 inside the sector as d pi. Yeah. Then the Taylor series is H hat Z.
Oh, but it's not convergent, right? Yeah, it's not the convergent because it has ZDU, which kills everything.
Yeah, because the asymptotic expansion is sort of a Taylor expansion in some sectoral region where the vertex of the sector is a critical point.
Yeah, I see.
Yeah. Okay, and then now let me tell you what are the most important two more propositions which characterize the Stokes phenomenon. So another thing is that the Borel summation depends on the direction D. Of course, we can vary this D. Then we get a priori we get different holomorphic functions, right? And defined on different sectors. Let's try to compare them. So let's take another, say D prime. So we can, of course, we can also do BD prime to get another solutions. And what are the relations? So let's simply redraw this pizza with boundary D and D prime. And then let's close them using this triangular. Then the Stokes theorem tells us that the integral around this, roughly speaking, around this triangular is 0. If you still remember what are the integral, that is exponential 1 over t minus t over z times gt and dt, and this is the integral, and we do this integral around this triangular, which is 0 because dt is holomorphic inside, right? The first part of this theorem somehow includes the fact that GT may only have critical point along these directions, right? Because it can be analytically continued to all the direction D, but there's finitely many anti-Stokes rays. Therefore, it's holomorphic inside. And then because around the infinity, GT is very, very small, then the integral along this outside ray is somehow 0. Or you can also use Jordan's lemma to show that the integration along D and D prime are equal. So that simply gives us the fourth property, which says that if two direction D and D prime, where you take the integration, are somehow bounded by two adjacent anti-Stokes rays, say di and di plus 1, then BD and B prime DH hat should be equal to each other. In other words, we can also say FD Z equals to FD prime Z in their common domain of definition, that is SD pi intersect with SD prime pi. Yeah, very good. And now, if we vary D furthermore, such that D prime curls some anti-Stokes ray, say, now if we take D prime prime, where D and D prime prime are not bounded by two adjacent anti-Stokes ray, these black rays, but somehow they are separated by one ray. Then what happens? We can still use a Jordan's lemma. So we have D prime prime, but somehow we have a Stokes ray, anti-Stokes ray inside, bounded by them. And as we said, GT, the function GT can have pole or critical point along this anti-Stokes direction, and it ends up using the Jordan's lemma. It ends up that the integration along D and D prime prime are not equal, but there are some contributions from the residues, right? I can give you some concrete examples later on, but now I try to convince you that somehow if, yeah, maybe after I say this, I give you a concrete example. So if somehow D and D prime prime are not inside one, are separated by certain anti-Stokes rays, then in general they don't equal to each other. The two solutions are not equal to each other, and this is actually the so-called Stokes phenomenon. Now let me simply give a summary of these 5 properties. Let me give you the summary what we are now. So remember that we are still solving this ODE, and we have drawn a picture like this. So this picture, this configuration is uniquely determined by U, by the diagonal matrix U. And then we have claimed that BD and BD prime, if they are in the same sector, then somehow they give you the same solution. That somehow means that we can glue, so this is gluing, we can glue all the FD Z for D inside, for D bounded by 2 adjacent Stokes rays. Yeah. So this is not quite right, but let's just use this to denote D varies in between of 2 adjacent Stokes rays, and then I glue all the corresponding solutions from borrow resummations, and they somehow, because they are equal to each other on their common domain, therefore they glue together and give you a function, holomorphic function on a bigger sector, and we call them the canonical solutions. So each Fi, so we define this as Fiz. So we have, again, let me draw this D0, D1, and so on, D2, and the DL plus 1, and so on. So so here is each of this Fi is a solution specified by 2 adjacent Stokes rays, Di and Di plus 1. As I simply take all the direction D in between Di and Di plus 1, and I glue all the solutions FD. And in the end, this is actually a holomorphic solution. So this follows from proposition 4. This is a holomorphic solution on a much bigger sector, sector I, which is given by Di minus 2 pi and Di plus 1 plus 2 pi. So it means that, so this is a sector where the most right edge is Di minus 2 pi. So for example, let's take I equal to 0. Then this is D0 and D1. So I draw a red line perpendicular to D0 and another red line perpendicular to D1. Then inside this is a sector region. d0 minus 2 pi and d1 plus 2 pi. So this red region is where the solution f0 is defined. I simply glue all the possible fd inside, bounded by d0 and d1. Okay. And then we know that fi is actually a solution on this sectoral region with opening bigger than 2 pi. Then there is a so-called Watson's lemma, states that if any solution of this equation has a prescript asymptotics h hat in a sectoral region with opening bigger than pi, then it's unique. Therefore, following from, yeah, I guess I'm too slow now. It's 50 minutes. I'm still sorry. Yeah, probably I gave too much.
Well, well, you are about, if you're halfway through, then it's okay. We actually have a bit more than an hour and a half, and besides this, you started a bit later than we originally were supposed. So yeah, if this is the middle of your talk, then it's perfectly okay. It's perfect timing.
Yeah. So yeah, I guess probably I'm a bit behind my schedule. Yeah, but still, let me finish this introduction with more detail. So then by let's just say it by Watson's lemma, fi is a unique solution. So there is some theory guarantees that fi is a unique, therefore canonical solution on sector I. For example, f0 is defined on the red region, sectoral region. Is a unique solution, holomorphism defined with a prescript asymptotics with a given initial condition, basically. That is fi z. Recall that from our proposition 2 and 3. So if we combine proposition 2 and 3 and 4, this is what we are doing now, right? Then we show that fi somehow times exponential 1 or u over z and times z power of minus a is asymptotic to h hat. But let's simply forget all the higher order terms. Let's simply say it's asymptotic to the identity matrix. As z go to 0 within sector I. So this is this is not quite uniform, but uniformly in any closed sector. But somehow we already proved that, not proved, but if we combine proposition 2, 3, and 4, we can easily see that fi do have this property. Then using Watson's lemma, it's unique. So any solution, any holomorphic solution defined on a sectoral region with opening bigger than pi, and at the same time have this asymptotics is unique. This is what Watson's lemma say about this ODE. Therefore, we get canonical solution because it's unique, which is important for us. Okay, very good. Okay, now until this moment, we basically know the structures of solutions to this ODE with a fixed initial condition. We proved the existence, but non-uniqueness for the solutions. So basically, we see the existence somehow, but non-uniqueness. Non-uniqueness is from the 0.5. Non-uniqueness of the ODE. That is F0, F1, F2, and so on. They may not equal to each other on their overlap. And now this non-uniqueness is basically Stokes phenomenon. And we want to measure this non-uniqueness. For example, let's take two solution, say F0 and FL. So let's try to see they're different. Take F0 and FL. Recall that L is the opposite. DL is the opposite direction of D0. So we can see this graph. Then the defining domain of FL is this guy. So this purple line is perpendicular to DL, and this line is perpendicular to DL plus 1. And then, so this purple region is where FL defined, right, by our definition. And they somehow have an overlap. The overlap is this region, which include, where I solid this region. And because in general F0, FL are not equal to each other, and they are the common solution. They are solutions for common linear ODE system. Therefore, their ratio must be a constant invertible matrix. All of the solutions are fundamental solutions valued in GON C. Therefore, their ratio, that is their ratio in the common domain of definition, is a constant matrix inside GON C. And this matrix, of course, measures the non-uniqueness of solutions with a given prescribed initial condition or asymptotics. And this matrix is a so-called Stokes matrix. This is the main object of this talk. So now we can introduce the so-called Stokes matrix. Let's call it S plus. By some reason, I will explain. It depends on U and A, the coefficient of the matrix, of the ODE. And the Stokes matrix is uniquely determined. So this matrix is basically a ratio of F0 and FL. So this is our solution, two solutions. And their transition matrix is a Stokes matrix. Yeah. And this identity is defined in sector 0 intersect with sector L. So basically this region. Basically this region I just painting here. Okay, and this is a so-called Stokes matrix, somehow measure the non-uniqueness of solutions. And from a different viewpoint, there are different viewpoints to the Stokes phenomenon, but I may not talk about another viewpoint, but just say this is a Stokes matrix. And let me write this is Stokes matrix. Until now, is there any questions?
Well, no, as far as I'm concerned, I'm quite satisfied. You're doing perfectly well. And,
yeah, very clear. Thank you.
Yeah, extremely clear.
Okay, great. Yeah, thank you. And then maybe let me give you some examples. You know, in this field, the difficulty thing is that nobody knows how to compute Stokes matrices in general. So this is the main difficulty in this field. But still, let me give you some examples. So let me see. But before that, let me, because I denote S plus somewhere, right? There is another S minus. So what is that? Because we are actually on the universal covering because the solution includes the Z power of A part. So we are actually on the log, on the universal covering of the log Z. so here we should take the branch of log z, and we can always take a continuation of FL to another branch. Then then FL and F0 gonna have overlap here. But here we should close some. You can say we can close. We have to go to another cover. Then we can take the ratio of these two solutions to get another constant matrix, which is a so-called Stokes matrix S minus. So eventually we get a pair of Stokes matrix. Yeah, I'm not really know it's plus or minus, but if we take a continuation of F minus to another branch such that they have overlap, then we can define another S minus. And in general, S plus and S minus are very different. They have no relations, no functional relations in general. Yeah, and this pair of matrices are called the Stokes matrices. And we can somehow compare Stokes matrices to the more familiar notion, like the monodromy matrices or connection matrices. Because that if we are given a linear system with regular singularity, like just some comparison, because it's comparison. So recall that if we have, for example, in Pont-Levi or whatever case, if we have a linear system where ABC and a constant matrix, then any formal solution of this system is automatically holomorphic. And that is very different from our case, right? Because our formal solution is indeed formal. And then the monodromy is simply you take a base point and you go around 0, 1, and 2, and so on. And this is the monodromy data we are interested in. But Stokes phenomenon, as we just outlined, is somehow local theory, right? So we actually talking about z equal to 0 neighborhood. So this is a very local thing, and at the same time, the Stokes matrices are some internal monodromy, right? We don't compute like in the regular case. We don't take the frame at a different singularity and then consider their connection matrices, but somehow we take the framing in each of these Stokes sectors, then compare their and then consider their connection transition matrices. That's Stokes matrices. So this is sort of internal data hidden inside the irregular singularity, the second order pole. Yeah. Okay. Right. And that is the introduction. And yeah, I guess I don't have time to talk about the model space, the Poisson structure model space. And now just let me directly go to the quantum group. And of course, like Professor Robzov and also his collaborators, I think Professor Chekhov and Mata Matsuko and many other people like Philip Boch and many other people, many people working on the space of Stokes matrices and the Poisson structures on it and so on. Yeah, but just for short, it's just mentioned there is some relations. There is some Atiyah-Bott construction, irregular Atiyah-Bott construction to study. People do care about the Poisson structures on the space of Stokes matrices. Yeah, from Riemann-Hilbert viewpoint. But now let me just switch to the quantum case. So in this case, sorry, yeah, I promised to talk about some examples. Yeah, sorry for that.
If you just in a hurry, can first talk about what you the presentation and then give examples. I mean.
Okay. Then probably I give you. I prepare several examples, but just tell you the most easy one, the so-called Euler series. But I guess many of you already know this, so I'll just forget about it. Maybe this is too standard example. Yeah, let's just go to quantum group. The example is simply compute explicit Stokes matrices of certain linear system. Okay, and now let's go to the quantum group side. So we take a universal version of the previous. So recall that before we have this system, and of course, matrix A has commutative variables. Let's simply, and you can think of A as a space of n by n matrices, which is a Poisson space, whose quantization is the universal inward looping algebra UGUN with the generators, say EIJ, the generators. So now let's quantize this space with a relation bracket EIJ EKL equals delta JK EIL minus delta LI EKJ, I guess. And so this A is AIJ should be single of the coordinates. AIJ is the coordinates on symmetric GUN, on GUN. And now we take a quantum analog. This is people in quantum system general do. So we take a quantum version. So we take n by n matrix T whose IJ element is the generators of UGN. So this is simply, we can say this is an element inside the UGN tensor with n the Cn. So for example, in 2x2 case, I simply have E11, E12, E21, E22. Yeah. I take a matrix whose entries are the generators of UGN. And at the same time, let's take U, again, a regular Cartan element. Say, in our case, diagonal matrices with distinct eigenvalues. So of course, this U can also be think of, because UGN is unital algebra. Therefore, each of these U1 to UN are elements inside the UGN. Therefore, we can also think of U as element inside the UGN tensor with endomorphism here. And then, given any highest weight representation of GUN or UGN, endomorphism L lambda. So this is the highest weight representation. We can associate to this data the KZ equation. The KZ equation. That is f is a function of z of dz equals to h times u over z square plus t over z times f. Now, the function in this equation is valued inside endomorphism L lambda tensor endomorphism Cn. So this is again n by n. You can think of this as n by n matrix valued function, but each entry is endomorphism on L lambda, and therefore this product, this dot, is given by the n by n matrix multiplication and the action of UGN on L lambda.
I'm sorry, what is L lambda here?
Representation, highest weight representation.
So it's just algebra, it's just the space. I see.
It's a
It's not
finite
just-
dimensional. It's a
Yeah.
finite dimensional.
Dimensional. Okay.
Yeah, finite
That's
dimensional.
strange. I mean,
Yeah.
So
Finite
Q and
dimensional.
T belong to endomorphism of Cn times universal enveloping. And
Exactly.
if the product,
Yes.
is this product taken in the sense of raw? I don't quite understand.
Yeah. Yeah. So here the product is given by, let me just wrote. So this product is given by this dot is given by, on the one hand, matrix product, on the other hand, given through the representation. And 0, yeah, GN. Okay. Oh, yeah, but this is actually you can simply think of this as a blocked linear system of ODs, right? So this is an n by n blocked, where each block is a dimensional L lambda small block, right? So you can think of, yeah. Therefore, this is actually a special case of the previous, OD. So this OD, if we think of this is a blocked, if we think of this as a sort of n times dimension of L lambda system of ODs. Okay. So this is a rank of ODs. And this is exactly one case of our previous discussion. Therefore, you can also study its Stokes phenomenon, like its formal solutions, and borrow resummation of its formal solutions, and to get holomorphic actual solutions on certain sector regions. And then you compare the solutions on different sector regions to get a Stokes matrix. It's again a pair of Stokes matrices. But the 8 Stokes matrices is now let's call it, so sorry, here I should say H is any non-zero complex number. Then SH plus minus are the Stokes matrices of this system is now an element inside. That's right, it's SH plus minus IJ. It's now an element inside endomorphism L lambda tensor with endomorphism Cn. That is, each of these small entry is an endomorphism on L lambda. This is simply because our system is blocked, right? It's a blocked system. Okay.
What is SHIJ? SH.
This is IJ entry.
So you just
This-
take Stokes matrices
Yeah.
and put them into this matrix, right?
Yeah, probably I here. So recall that our system, our solution is valued inside this vector space, right? And their ratio is, of course, also living inside this vector space, which is where the Stokes matrices should live.
I thought it was in endomorphism of Cn where it took values.
Yeah, but the thing is that, this is not an n by n system. The rank of the system is n times, right? Because our system has much larger rank.
The Stokes system?
This system, this ODE.
The one which you written here at this page, right?
Yeah, this ODE. Before it's n by n, of course, but now this ODE.
I see.
This ODE, because.
Oh, you regard it as a Stokes system with just this strange dimensional
Exactly.
condition.
Exactly. So actually, it's a linear system where each variable is non-commutative. Yeah, but somehow more convenient. More conveniently, you can think of this as a block system. So this is like an n by n system, but somehow each entry is again a m by m system. So in total, it's n times m rank.
I see.
Yeah. This is safe. Yeah. Okay.
Sorry, could you recall what is the meaning of H? What is the role of H here?
Yeah. Here H is a Planck constant. I will explain. But now at this moment, H is simply a non-zero complex number. Any non-zero complex number.
Yeah, I understand. I just want to understand. So it's like a parameter which will go to zero later, right?
Either zero or infinity for different reasons. Go to zero to get the classical like Poisson structure. Go to infinity to get the crystal structures. I gonna say it now soon. Yeah.
Okay.
Okay. So yeah. So far so good.
Perfectly nice.
Yeah.
You still have about 20 minutes at least.
You
still have about 20 minutes at least. About
okay.
At least even more, I think, because we started later.
Okay. So basically, in this page, I take a representation of GON, and then I take a regular Cartan element U. Then I take this OD, which then associated to this data, I consider this OD and its Stokes matrices. And this is sort of standard. Just as before, we can take its Stokes matrices. There is no. So this is.
Stupid question. Can you regard these block matrices as just the solution inside, not the tensor product of endomorphism algebras, but their solution inside the tensor product of endomorphisms of Cn times universal enveloping? Can you replace endomorphism of L lambda with just universal enveloping here?
It's a good question. In some sense, yes, yeah, but for our method, maybe not, yeah. I gonna say it, yeah, because UGLN is not it's infinite dimensional, and for all this holomorphic, thing work, you need a Banach space to talk about complex analysis. If you have UGLN, you can, but you may need H to be a formal Paul. You may need H to be a formal Paul series to get extra grading on UGN, and each grading, each of the filtration is finite dimensional. But somehow that is very different from the finite dimensional setting we used here.
Yeah.
But somehow this is still universal, in a universal sense. Yeah. But to really use Borel summation and so on, it's better to stay in the finite dimensional setting. Yeah. Okay. And okay, great. Now we can state our first theorem. So the theorem basically says that for any fixed H, as Professor Regulov asked, so this is an element, and any U, which is a regular Cartan element, the following map. Here I should let Q, I introduce a new parameter Q to be exponential pi H. Then the following map as SQU, a map from Greenfield-Jimbo quantum group, UQGUN to endomorphism L lambda is a representation of quantum group on the same vector space. Recall that before this is simply a representation of GUN. And the maps the generator of UQGUN to the entries of Stokes matrix SH plus U, the off diagonal the ith row I plus 1 column element, and similarly Fi to the SH minus U I plus 1 I. So recall that the entries of Stokes matrix is element in endomorphism of L lambda, right? And here, I forgot to say that the Stokes matrices have triangular properties. I can always, up to a gauge transformation, I can always assume S plus is up triangular, while S minus is lower triangular. Yeah, but some more details, but yeah. And this theorem says that this map somehow defines the representation of UQG Ln on the same vector space, finite dimensional L lambda. Yeah, I don't know here if I should I recall this quantum group, but this is the Dreamfield Jimbo quantum group. Is associative algebra with generators. Generators. E1 to E minus 1 and F1 to F minus 1. Sorry, F1 to Fn minus 1. And then because I'm in GUN, and then I have Q power of pi I hi. Some people denote this by capital Hi or Ki. Yeah, this is I from 1 to n. I have one more because it's in GUN, and with some relations. I may not rewrite these relations, but these are the Searle relations where you replace integers by quantum integers. There's relations. Some quantum Searle relations. These are the these are the generators. Okay. Right. And this theorem basically says that the Stokes matrices, for example, they are off-diagonal elements satisfy certain quadratic algebraic relations. And or equivalently, it says that the Stokes matrices somehow satisfies the so-called RLL relation in the FTR reformulation of the quantum group. Yeah. Probably just give a remark, short of time remark. So it's also equivalent to that S satisfy the so-called RLL relation. S. Yeah, and you have another one plus and minus, right? So this is the first theorem.
So can you explain what is the difference between SQ and SQ is the map is given by SH, right? I see.
Yeah. Sorry, yeah. Let's call it mu, because normally people using mu.
Yeah, because it's a little bit confusing when you have both.
Yeah, but I cannot write mu because it looks like U. Let's call it.
Because the long. Yeah, actually, it's different. Mu has a long first leg, and then it goes like U. So it's U with long first leg in front of U. So it's different, but
New like this. This is new.
This is eta, but it's also okay.
Okay, yeah, let's call it eta. Right. Yeah. Yeah. All of a sudden I forgot what nu looks like.
Oh yeah, I see.
Yeah. But people do use nu to denote Riemann-Hilbert map. But this is sort of the Riemann-Hilbert map. Yeah. All right. So okay. Now the interesting sorry. Yeah.
Our matrix, what kind of R matrix do you have here?
This is standard R matrix.
The one which appears in definition of UQ or something different?
Yeah. This is a standard R matrix from appearing in the definition of UQ.
In particular, it means that the elements of SH, they actually commute. Oh, great. Oh, thanks.
Yeah, this is from quantum Toda, for example, in Professor Jimbo's paper.
Yeah, I see. Very nice.
Okay. So the interesting thing for us is to understand, to try to understand. Our goal is try to understand or to study the Stokes phenomenon. But in general, Stokes phenomenon is much more, general. It's not only about the linear system. One can talk about PDEs and nonlinear equation and so on. But we are basically studying the Stokes phenomenon of linear system. And even with more constraint, like with the power of order 2. So this is the simplest case where Stokes phenomenon can happen. A linear and the power of order 2. Power of order 2. Power of order 2. Of Poincare rank 1, or in other words, order 2. Yeah. So this is the simplest setting where the Stokes phenomenon arises. And we would like to understand the Stokes phenomenon somehow using the representation theory of quantum group from the algebra structures. Yeah, let me just tell you what it is. So there are many questions which is not quite clear in the Stokes phenomenon of this system, like the WKB analysis and the Soliton solutions and many other things. And let me show you how this analysis problems is related to quantum groups. This also answers a question, not answer, but it's related to the question of Professor Regulov. So so there are several things, but let me first say the canonical basis thing. So recall that what we do is basically given, so this is UGUN, and given a finite dimensional representation of UGUN. So this is what we call rho, and then using by some analytic way, solving the ODE using the Stokes phenomenon, we get a representation of UQGUN on the same vector space. So this is by what we called eta QU. Depends on, it's parameterized by U. Yeah. And now, on the one hand, the quantum group, or the positive part of the quantum group, is equipped with a canonical basis discovered by Professor Lustig and Kashiwara. So it has the canonical basis. The canonical basis, let's call it B. Then we can let the canonical basis, the set of elements acting on through the representation, it can acting on the lowest weight vectors of L lambda. That is by acting on the lowest weight vector of L lambda. the image of the canonical basis through the representation of either QU will give you elements. A set of vectors inside A lambda. Let's call it BQ U lambda. Set of vectors inside A lambda. Okay. Now our conjecture states that this set is actually for any q from 0 to infinity. This set is actually a basis of L lambda, and in particular, as q goes to 0, this set coincides with the eigenbasis of the shift of argument subalgebras.
Doesn't Q go to 1?
Q go to 0 maybe, yeah.
H
because
goes
because Q equals exponential pi h.
Yeah, it should go to 1.
Yeah,
Not
go to
to
1 is a classical UGN, undeformed UGN, but we are talking about canonical basis. That is Q go to 0 or infinity. That is H go to infinity or.
I see. Sorry.
Yeah.
Okay.
Yeah. Yeah. But this can be proved in 2x2 or 3x3 case by hand. But the interesting thing is that it somehow gives you a continuous path between canonical basis and eigenbasis of shift of argument subalgebras parameterized by same U.
I'm very sorry because I interrupted you. I didn't catch the point. I'm sorry. Can you just repeat the statement? As Q goes to 0, what happens to this set?
Yeah, I don't want to formulate this conjecture because this is far from
Conjecture.
I just let me give you a conjecture which can be proved, which has been proved partially. Yeah. But this somehow says that under this map, Stokes map, the canonical basis somehow becomes the eigenbasis of shift of argument subalgebras parameterized by same U. But I will not write this. And somehow it's very interesting because it gives a continuous path between canonical basis.
What do you call shift of the argument?
Yeah, so this is.
Sorry, what algebras do you call shift of the argument? Classical ones in the Poisson?
Quantum one.
In UGLN?
Yeah. But here, if to be more precise,
what construction of the shift of the argument matrices do you use?
To be more precise, yeah,
constructions, like for instance, you can. I mean, they all give more or less the same thing, but for instance,
yeah,
you can take Tarasov's construction where you just take the symmetrization of the classical canonical just this, or do you use some kind of Fagan-Frankel generators and pull the universal envelope in using Rybnikov's construction?
Right here. So if I to be more precise, I have to take U to be real points, to be real part of each regular. Then following, as you said, Fagan-Frankel and Rybnikov, we know that the shift of argument parameterized by U has simple spectrum. That is, therefore they have eigenbasis. Yeah.
So you just take the Fagan-Frankel-Rybnikov construction of the shift of the argument matrices algebra, right?
Yeah. Then I need the fact that they have simple spectrum. Therefore, you can talk about eigenbasis. Yeah.
I see.
Yeah. Because we but probably let me tell you some approximation to this thing, which can be more clearly formulated and can be proved in one case, and which is more interesting to me because it involves the WKB analysis of the ODE. So So again, let me rewrite the equation. So the equation looks like, the ODE looks like this thing. It can be, so this is ODEs we talked about, and the Stokes matrix is somehow is related to the quantum group representations. And now the thing is that on the one hand, as Q go to 0, we know that the quantum UQGUN can be characterized by some combinatorial structures like the canonical or crystal basis. They're canonical or crystal canonical basis. And on the differential, on the analysis side, as Q go to 0, that is as H go to infinity or I times plus infinity. Then this is actually the WKB type analysis.
What does it mean with WKB?
Yeah, that's me. So WKB, first WKB stands for three mathematics or physics name. And it's a method. It was introduced to solve the Schrödinger equation in a perturbative way. And whenever you have a differential equation, you can put a small parameter epsilon in the front of the highest differentials. Like in our case, we can simply move h to the left, then we get 1 over h, right? And then h go to infinity is the same as 1 over h go to 0. And this type of analysis is what I called WKB analysis, because in the Schrödinger equation, I guess this is a one-dimensional Schrödinger equation times potential times phi. And then this method was designed to solve in a perturbative way, to solve the Schrödinger equation as a power series of h hat. Yeah. And you can see the similarity between these two things. So on the one hand, the quantum group.
Oh, actually, here it's h bar squared on the numerator, not the denominator.
Oh yeah, sorry. Of course, it's multiply a small number. Yeah, right. Thank you. Yeah. But see, this is our h and is
small, of course.
Really 1 over h. Yeah, it's a bit. Yeah. Okay. Okay, and it motivates a question that to study the epsilon go to 0 or 1 over h go to infinity, go to 0 or h go to I times positive infinity, asymptotics of the Stokes matrices. And one should expect that this asymptotics is characterized by crystal structure, asymptotics of the Stokes matrix, which is, or let's say its element, then each of its elements is endomorphism of lambda. Yeah. Okay. And from it, recall that, for example, if we take the off-diagonal elements, let's say, let's denote off, so some off-diagonal elements, then this is a this is the Schauer generators. And then the h go to I times infinity asymptotics is exactly the q go to 0 asymptotics. Therefore, we should see the crystal structures, at least in some heuristic sense. And now we want to make sense of this statement. Then we make up the following conjecture and prove this conjecture for a special U. And the conjecture, as I just said, it basically says that for any U, a regular Cartan element, there exists a sort of canonical basis. Let's call it Vi, parameterized by U of U lambda. And operators EK tilde U, FK tilde U, this is gonna be the crystal operators, where K is 1, 2, and -1, and such that for any K, for each K, there are constants C, let's say CK prime, such that the leading asymptotics of Stokes matrix is given by the operator EK tilde FK tilde. That is limit Q equals exponential pi I H go to 0 power of Q power of constant CK times the Stokes matrix K plus 1 element. And then, so this is an endomorphism. Therefore, it can acting on the basis. And the limit exists and equals to EK tilde, the operator acting on the basis element. So this I is living in some index set. And similarly, so this basically says that the Q go to 0 or H go to I times infinity asymptotics of Stokes matrix is characterized by operators acting on a basis. And
this
similarly,
VI, it's the same collection of vectors you already told us about. With this,
this is a part of the.
You expect VI to be given by this B that you showed us before.
Not B, but the eigenbasis of shift of argument. Yeah, I gonna write it. This is part of the conjecture. So this goes to FK tilde VI. So the first part says that the conjecture, first part of conjecture it says that there exists combinatorial descriptions of the H go to infinity asymptotics of the Stokes of diagonal elements of Stokes matrices, and the combinatoric object is a basis and the operators on it. And furthermore, this combinatorial structures is actually a crystal. Furthermore, the sort of WKB, I call it WKB datum. It's actually, so this is a finite set, the basis equipped with 2n-2 operators. All of this is depending on a fixed U, regular Cartan element. And this is actually a GUN crystal. So GUN crystal is just a model of the basis of the base. Yeah. Let me see. Yeah, I mean. Yeah, I read. Yeah, I guess my time is up. So I just say the GUN crystal is it's a model of the crystal canonical basis. It's a finite set. This finite set model on the basis, and these operators. This operators model on the Kashiwara crystal operators, and there is a parameter. It gives a parameterization of the combinatorial information of the basis. All right, and furthermore, as you mentioned, and it's furthermore, it's isomorphic to the GUN crystal introduced by During crystal. During crystal, right. Sorry, I have this is isomorphic to the Geon crystal. Introduced by HKRW that is Halachiva, Kamnitzer, Rybnikov, and Weeks. Yeah. So probably I should explain a little bit what their construction first. So basically, these people consider, as I said, so they take the shift of argument subalgebras, but to be more precise, this U should be real points in regular Cartan. Then this guy acting on L lambda will have the simple spectrum. Then they take the eigenbasis of this simple spectrum. The eigenbasis will give you a cover. Then the eigenbasis is a cover. It's a finite set. It's a cover over the space of H, the real point of H reg. But at the same time, I guess in the paper of Finken-Frankel and Rybnikov, they prove that this commutative subalgebra somehow extends to the decontinuity process compactification of this H regular. And similarly, this eigenbasis extends. Yeah. And for example, in this H regular, so if we take the decontinuity process space, because my time is up, let's just say it. So this space has a stratum. It's a stratification, and the zero dimensional stratum has some special points called caterpillar points, and at the caterpillar points, the shift of argument subalgebras become Gorfan-Hattin subalgebras, while the eigenbases become Gorfan-Hattin bases. Yeah, there are some particular caterpillar point where the eigenbasis becomes simply the Gorfan-Hattin basis. Yeah, and there is a Geon crystal structure on Gorfan-Hattin basis, and their construction is a cover. It's a sort of flat section. It's a local system, and then the local system somehow the parallel transform push forward the crystal structures to each of the U point, and eventually one can compute the monodromy representation of this cover, which gives you the pi1 of the decontinuity process space of H regular R, which is a characters group. So eventually one get characters group actions on these crystals, Geon crystals. And this is the Geon crystal I'm talking about. And recall that in our story, we also have this U parameterized by regular Cartan part. And actually one can also see the characters group actions out of the Stokes matrix, because to define the Stokes matrix, I have to pick some discrete choices. Like I have to take the initial sector, I have to take a branch of log Z on it. And somehow these discrete choices, before I taking the Q go to zero limit, these discrete choices give you the bright group actions on the space of Stokes matrices. And as long as I let Q go to zero, the Stokes matrices, the asymptotics becomes this discrete data, and the bright group action somehow degenerate becomes the Cactus group actions on these crystals. Yeah, and this conjecture somehow states that the Q go to 0 or H go to infinity asymptotics, the so-called WKB approximation of the Stokes matrices is characterized by GON crystal, and the GON crystal is unique. Yeah, therefore it gives a description of what are the WKB approximation of the analysis problem. And this conjecture is proved for a very special U, basically as U at the caterpillar point. But I guess I will not comment on it by solving some explicit Riemann-Hilbert problem. And for me, this is interesting because the WKB analysis of linear systems with rank bigger than or equal to 3 is not very well understood. And this conjecture somehow give you characterization of their WKB approximation, and it also has a classical version, which is conjecturally which can give some new ideas to the WKB analysis problem. Yeah, sorry for taking time. I guess
just think that the final part of your talk should probably constitute a separate talk, because it's really very interesting, but there are lots of things that really need some clarification, like the definitions of crystal structure and so on and so forth. It was, well, it's really very interesting, but
thank you. Yeah, I guess I just stop here. Yeah, thank you. Thanks for coming to my talk.
Thank you for talking to us. So just we're really very late now, really much, but I think there is some time for a short question. If there is some if you have a question, you are free to ask some short question.
Yes, please.
Is there any question? Okay, just as far as I'm concerned, I really have lots of questions. But can you just give me the reference to the Jimba paper where he speaks about the relation between the Stokes matrix solution and the how do you call this, and the R matrix equation, this Yang-Baxter equation, the one just which you mentioned.
Okay, of course, I'm gonna send you. You mean this RLL?
Yeah. This one. Yeah. No. Up. No. Yeah. Here it is. Yeah. This one. Yeah. This one.
Okay. Yeah.
No, you meant that you said that it was somehow related to appeared in Jimba paper.
Yeah,
and,
but
it looks like some solution of Yang-Baxter equation inside universal enveloping matrix. Because if you that's what I mentioned, because you can actually regard, if you forget about the infinite dimensionality of UGLN and regard the solution of the Stokes equation as an element in the tensor product of UGLN and endomorphism of Cn, then it is just the solution of Yang-Baxter in this algebra. That's
right.
Really, and that's why I really would like to see it. Okay.
Of course. Yeah. And this formulation appears in Nikolai's paper, right?
Which one?
Quantization of Lie groups in 80 with 80 something. Yeah, I gonna send you
this formula. This TTR equal to RTT. Yeah, I know. I see.
Yeah.
It's not in that context. It's in some. They just have this equation and then just it's built on it. They construct quantum groups.
Right.
Out of this. So I just want to see how this equation actually appears in the universal enveloping algebra context. That's what. So if you have this reference, I'll be very grateful.
Okay.
Thank you. Yeah, in advance. So any other questions or comments from the audience?
Mhm.
Well, if not, then
Yes, the last part, yeah, the last part of the talk was really interesting. I remember you also mentioned some shift argument algebra. Can you comment on this, or maybe Yorgos can comment?
I mean, this argument shift algebra is a subject you can talk about for a very long time, actually, in this context. Just the construction is quite involved. You see, there are several constructions. Each of them, none of them is satisfactory, in my opinion. Yeah, there are several. And as far as this one is concerned, I think Professor Su mentioned that he builds on the Rybnikov construction, which derives from the Fagin-Frankel center of the Katz-Moody algebra. So this is a very quite complicated one, but yeah, it's probably the most functorial one out of all existing constructions. I mean, Moliev's constructions are very nice, but he just gives you explicit formulas, and it is hard to say if these formulas can be somehow related to each other. He gives it in different classical series, but yeah, just comparing them is not very easy, I would say.
Yes. So basically, if this term disappear, if 1 over h go to 0, what left are the shift of argument, right?
Yeah, it looks like that.
Yeah.
Really.
Yeah.
And
but yeah.
That's
but
why
somehow,
I was Jimbo Miwa. Jimbo.
Yeah.
Papers.
Okay. Okay.
Looks like some very functorial way to derive this without resorting further to I mean, it might give you a way to construct with argument algebras without resorting to the Katz-Moody algebras, seeing just totally within the framework of universal enveloping. That seems to be just kidding. Okay, sorry for.
Yeah, well, actually, if you solve this equation in a formal way, then you have some recursive relation, if you remember. Then the recursive relation, my student Qian Tang, you met him several times, so he showed that the recursive relation is actually of course it's a difference equation, and the coefficient of the difference equation satisfies some Yangin's relation, sort of. There is some Yangin
Yeah, I really would like to see this, but while I'm still here, I just like to have this discussion once. Okay, just let us. I think the audience is already a bit tired. So if there are no other questions, comments, other than my Professor Zheklov's, and since we are here in China, we can still talk to Professor Su in person. And since there are no other questions, I think it's time for us to thank our speaker again for a wonderful talk, actually.
Okay, thank you. Thanks again.
I just hope we shall have another opportunity to continue, because the last part was a little bit, you didn't have time to end on this.
Yeah.
Maybe
we hope to hear you again.
Thank you. Yeah. Thank you for coming to my talk.
And just announce this seminar over, and let us meet again in a week. Again, thank you for coming.
Okay.
Bye.
Bye. Take care.